Hi all, I am Anjusha KV. Today I am going to discuss about the concept of bending moment and shear. This is the overview of my presentation. An introduction. Shear force is the algebraic sum of the vertical forces at any section of a beam to the right or left of the section, and it is briefly written as SF. Bending moment is the algebraic sum of the moments of all the forces acting to the right or left of the section, and it is written as BM. And the types of beams. The first one is cantilever beam, a beam which is fixed at one end and the other end is free. Figure A shows a cantilever beam. The distance between fixed and free end is called the length of the beam. The second one is simply supported beam. As you can see from the figure B, a beam which is freely supported at both ends is called a simply supported beam. The term freely supported means that the end support exerts only the forces upon the beam but not the moments. Therefore, there is no restraints offered to the angular rotation of the ends of the beam at support as the beam deflects under the loads. The third one is overhanging beam. As you can see from the figure C, the beam freely supported at any 2 points and having one or both ends projected beyond these supports. And the fourth one is fixed support. A beam whose both ends are fixed or built-in walls is known as fixed beam. And fifth one is continuous beam. A beam which is provided more than 2 support as shown in figure D is known as a continuous beam. Figure F is a propped cantilever. Here cantilever beam with a roller support will be there at the free end. Types of loads. It can be mainly classified into concentrated load, uniformly distributed load, uniformly varying load and concentrated moment. The first one is concentrated load. This type of loads acts relatively on a smaller area. Example, the force exerted by a chair or a table leg on the supporting floor. Figure A showing a beam in which concentrated load is acting. Here these two loads acting on the beam can be represented as W1 and W2. The second is UDL or uniformly distributed load, which is spread over a large area. Load is expressed in Newton per meter or kilonewton per meter. Example, the water pressure on the bottom slab of a water tank. For convenience, UDL is always converted into its equivalent concentrated load acting at the center of gravity of the loading. For example, in figure, W kilonewton per meter UDL is acting in the beam of length L. It can be converted into an equivalent point load of WL kilonewton acting at the middle of the beam. And the third one is uniformly varying load or UVL. This type of load will be uniformly varying from zero intensity at one end to the designated intensity at the other end. Example, the water pressure distribution on the wall of a water tank. As you can see from this figure, it is a beam which is subjected to a triangular block of brickwork. Here also equivalent concentrated load is to be used while dealing with this load. In this figure, W kilonewton per meter UVL is acting on the beam of length L. This equivalent concentrated load will be the area of triangle. That is, the formula for the area of triangle is half BH. That is equal to half into L into W. That is WL by 2. Which act at the centroid of the triangle, that is L by 3 distance from the left side of the beam. And the fourth one is concentrated moment. If for some purpose a beam is to accommodate a load on a bracket mounted on it, that gets transmitted on the beam is a concentrated moment as shown in figure D. Types of supports. Beams are supported on roller, pinned or hinged, fixed or simple support as shown in the table. In roller support, reaction force acting will be vertical. Here the beam can move along the horizontal direction and rotate at the support only it is restricted to move in vertical direction. In hinged or pinned support, reaction force acting in horizontal and vertical. At the hinged support, the beam does not move either horizontal or vertical direction, but beam can rotate at the hinged support. In fixed support, reaction force are horizontal, vertical and moments. At the fixed support, the beam is not free to rotate or move along the horizontal or vertical direction of the beam. Therefore, 3 reaction components will be there. In simple support, if one end of the beam rests in a fixed support, the support is called simple support. The reaction of the simple support is always perpendicular to the surface of the support. The beam is free to slide and rotate at the simple support. Shear force and bending moment at section. Consider figure A. This is the beam which is subjected to 2 point loads W1 and W2 acting downwards and reaction forces RA and RB acting upward to the beam. When dividing this beam into two sections, in the left portion of the beam at section, shear force will act downwards and right side shear force will act upward direction. In figure B, in case of bending moment at section XX is equal to reaction into momentum, that is equal to W by 2, which is acting at the support C into X. And sign convention of shear force. To the right side of a section, external force acting in upward direction is treated as negative. To avoid the confusion, we can remember the concept like this. Run, R-U-N, right side of a section, upward force is negative. Downward force acting to the right side of a section be treated as positive. The sign becomes just reversed when we consider the left side of the section. The same you can see in this figure. Sign convention of bending moment. Positive bending moment, internal resistive moment at the section that would make the beam to sag is treated as positive. A sagged beam will bend such that it exhibits concave curvature at top and convex curvature at bottom. Negative bending moment. The internal resistive moment that would hog the beam is treated as negative. A hogged beam will show convex curvature at top and concave curvature at bottom. To avoid confusion, we can remember the concept like this, as you can see from the figure. If the sagging bending moment is there, then it is like a happy face, that is positive. If the hogging bending moment we consider, then it is like a sad face and that is negative. Then variation of bending moment diagram and shear force diagram. In case of point load, shear force will be constant and bending moment will be linear. In case of UDL, shear force will be linear and bending moment will be parabolic. In case of UVL, shear force will be parabolic and bending moment will be cubic. This is a problem. The question is simply supported beam of length L meter carries a point load W kilonewton at the middle of the beam. Draw the shear force and bending moment diagram for the beam. This is the figure that I mentioned in the question. And first of all, we have to draw a free body diagram of the beam. Then in the point A, which is a hinged support, therefore there will be a vertical force as well as a horizontal force, VA and HA. And in support B, there will be only a vertical force because it is a roller support. The first step is to calculate the support reaction. Consider the equilibrium. Then sigma f of x is equal to 0. There is no external horizontal force in the beam. Therefore, HA is equal to 0. Sigma f of y equal to 0. Here VA and VB are acting upward and W is acting downward. Therefore, VA plus VB is equal to W. And take the moment about A. Then W will be acting in the W into L by 2, which is acting in the clockwise direction, therefore I put it as negative. And VB, which is acting in anti-clockwise direction, therefore it will be plus. Then we will get VB is equal to W by 2. When substituting this VB value in first equation, then we will get VA is equal to W by 2. When we are drawing the reaction forces W by 2 in the free body diagram, then we can draw like this and we can divide it into two sections, AA and BB. Step 2. Take the section AA and here this is the left part of the beam. Then shear force will be acting downward and moment will be anti-clockwise direction. And then sigma f of y is equal to 0. Then W by 2 is acting upward and V is acting downward. Then we will get V is equal to W by 2. And take the moment about section AA. Then W by 2 will 2 into XA, which is acting in clockwise direction, therefore it will be negative, and M will be acting in anti-clockwise direction, therefore it will be plus. Then we will get M is equal to W by 2 into XA. And the step 3 is take the section BB. If we are taking a right portion of the beam, then the V will be acting upward and the moment will be in clockwise direction. Then by solving sigma f of y and sigma m about b, we will get v is equal to minus w by 2 and m is equal to w by 2 into xb. And now we can draw SFD and BMD. While drawing SFD, we have to consider 4th equation and 6th equation. First, we have to consider the left side of the beam. Then left side of the beam, v is equal to w by 2, that is, it is a positive value and we can draw like w by 2. And then when considering the 6th equation, v is equal to minus w by 2, so it will be minus. And then when we are drawing the bending moment diagram, we have to consider 5th equation and 7th equation. First of all, at the left support, then xa will be is equal to 0. When xa is equal to 0, m will be equal to 0. Therefore, in bending moment diagram, bending moment will be 0 at left support. And when considering xa is equal to L by 2, that is at the middle of the beam, then we will get m is equal to w by 2 into L by 2, that is wl by 4. Next, if we are considering the 7th equation, when xb is equal to 0, that is at the right support, then m is equal to 0. So we can draw like bending moment is 0 at the right support. And if we are putting xb is equal to L by 2 at the middle, then we will get m is equal to wl by 4, that I draw in this figure. This is the BMD and SFD of the some common beams. The first one is simply supported beam with point load. The second one is simply supported load with UDL, and then cantilever with UDL. Then simply supported beam with a point load which is not in the middle, and a cantilever with a load at the free end, and a simply supported beam with 2 point loads at L by 3 distance from the support. Thank you.